started. Parham, you're muted. We cannot hear you, Parham.
How about now?
Yes.
Is it better? Is it good? Can you hear me well? Okay.
Yes.
Perfect. Well, thank you very much for arranging this, Amir, and thank you very much, everyone, for the introduction. It's great to know we have such a vast diversity of audience here, and that's what we really want for this lecture, because we want input from everybody. Quantum computing field is kind of at its infancy, so feedback from all of you and involvement from all of you is really valuable, and that's one of the reasons we are having this lecture today. So I'm gonna start with a lecture, like a presentation. Feel free to interrupt me anywhere in the presentation. I don't have access to share my screen.
I think you should be able to share. Try it on.
Yeah.
I think you can share it now.
Okay. It's still, it says disabled participant screen sharing. Yeah.
That's weird. Oh, okay.
Okay, now it works.
Okay.
Perfect. Okay, I'm gonna expand this. Yeah, so I'm gonna go through this lecture. If you have any questions, please feel free to interrupt me, and hopefully there will be time left for your questions, regardless of your background. There will be something in quantum computing, if not now, in the future, that will be relevant to your field. So, okay, let's get started with some personal introduction. This is my first introduction to science and quantum. So when I was my first introduction to science and quantum was when I was like 4 or 5 years old. There was this book series called 5 Treasures, and there was a biography of different scientists. Among all of these scientists, the one that really got my attention the most was this guy called Avicenna in West, or in Persian we say Abu Avicenna. I was very inspired by his scientific approach, curiosity, and how he explored different sciences. And a couple of years after, maybe when I was 5 or 6, I found this book that I really couldn't understand, but I could go through the pictures. And I got introduced to some of this relativity, entanglement, and some modern physics concepts through these pictures, very, very basically. And the reason I'm sharing this is I want to highlight the importance of early education. I'm going to talk a little bit more about it in the next slides. But fast forwards 20 years, 15 years after that, I started getting a degree in electrical engineering, and then I did my master's in nanoelectronics at Europe. These are some of the labs that I used to work. The left one is called IMEC. So I used to work there on next generation of transistors with companies like Intel and Samsung. So we used to work on incorporating quantum materials like graphene for making faster computers. Then I went to Sweden and I worked at the Chalmers University on spintronics to make computers more efficient and make more better memory devices with spintronic applications. And then when I started my PhD at University of British Columbia, I was very excited about these topics and this field. So I would use any opportunity to share my passion, and I would go to different classes and teach either quantum computing or nanoelectronics, especially the more modern or recent topics. And there was a lot of good feedback from students. I took a 1-year program in teaching at UBC to incorporate more active learning elements like demos in the class and engaging learning tools. So the students really liked it, and it was a really good experience. So after that, we started working on some expanding the quantum computing education projects. It is believed in the quantum computing field that in the next 5 or 10 years, there will be a significant shortage of talent because quantum computers are getting faster and faster and more efficient, but the talent is not growing as rapidly. So this is one of the projects that we proposed, and the idea was to tackle this diversity challenge very early on, before it's too late in Canada. And the other important part of this proposal was to tackle the issue of diversity. So if you're from engineering or at the university or at your work, you know, it's not the most diverse field. So we wanted to tackle this issue, especially in quantum computing early on, by giving access to quantum computing more to public, to indigenous communities, and also going to the schools, high schools, elementary schools, even down to hopefully kindergarten level at some point, to teach the quantum computing. And we built interactive web-based tools, educational tools that use real quantum computers at 15 millikelvin, minus 273 degree. We built, I think, the first mobile app that used real quantum computers to walk people through activities that they can learn about quantum computing. And we actually worked on a course for high school in Canada. So students at high school can learn quantum computing as a part of their curriculum and get credit for it. This will come in 21 and 22. And so far we have reached over 1,000 learners, and almost half of our learners are girls. And this year we are hoping to reach, after COVID, we hope to get a better reach into indigenous communities. Okay, so this was the introduction. Now let's get to the quantum computing part. And before we get to quantum computing and understand why we need quantum computing and what is quantum computing, we first need to understand what is the problem with classical computing, right? So a lot of you are experts in this field, data scientists, software engineers, and you all know whatever we have, our computers, my video, pictures, audio, at the end of the day, it's coded in a certain language, Python, C++, Java. And if you break that down that code, you will get probably to get some compiler language. And if you really go down deep into the code, at the end of the day, you have gates. And if you go even deeper, you have zeros and ones. Now, the question is, there are different reasons why we have zeros and ones, but the question is why classical computers are built based on the zeros and ones. And I am open to get some answers from audience. It's a simple question, but it helps to think about what is wrong with classical computing and why we need quantum computing. So type in the chat box the reason behind why the fundamental part of classical computing is zeros and ones. Why it's not 0, 1, 2, why it's not 0.51. Okay, Ariane is saying because transistors can only have two states, open and closed. Excellent answer, yeah. So the reason classical computers are built of zeros and ones historically goes back to the invention of transistors. So all of our computers, laptops, mobile phones, even your washing machine or dishwasher, the computer has transistors in them. And these transistors work like a switch. So they're either 0 or they're either 1. And back in time, they used to be quite large, maybe a couple of micrometers or centimeters. But nowadays, they're super small. The modern transistors are 20 or 10 nanometers. Does anybody know what is the latest transistor size in your mobile phone or computer? Sina is saying 3 nanometer, Ariane is saying, oh, our audience is really expert here. So can you imagine these transistors are nowadays 2 or 3 nanometers, and one of the reasons behind that is that we need so many of them to make complicated computation. So we need trillions of them or billions of them in our computers to make efficient computations. So as Aryan and Sina mentioned, we are down into the 2 nanometer node. And in order to make our computers better, we need smaller and smaller transistors. Now that we are in 2 nanometer, the question is how we can get even smaller. I mean, an atom is less than a nanometer. So 2 nanometers, we're talking about a couple of atoms. So this is a really big challenge. So the chip manufacturing industry in the past 10 or 20 years is really anxious and stressed about what to do once we get to this super small stage and what to do after that. Because the economy of electronics and a lot of industries are really tied into improvement in the performance of electronic devices. So we are almost getting to the dead end in the improvements of classical computers in terms of chip manufacturing. And in order to resolve that, we need new materials, new devices, and new computation. And that's one of the areas that quantum technologies can help us move forward our progress in computation. So I repeat, new materials, devices, and computation. So quantum technologies have different arms. You can use them for sensing, you can use them for communication, you can use them for computation. So this is one of the challenges of classical computers and one of the reasons we need quantum computing. I hope that was a good motivation for quantum computing, but we're not going to stop there. For those of you who are not into hardware or electrical engineering, we have another example of limitations of classical computing. You all know this thing, it's COVID-19 virus. And we all know that we had to wait a long time for a vaccine. One of the reasons behind the long wait for a vaccine is that we cannot simulate these complicated viruses and molecules and biological compounds using our classical computers. So in order to be able to simulate them, what we can do is that we can basically break them down into smaller parts, right? So anybody knows what is a virus is made of? I'm not really, I don't have any experience in this field.
Me neither.
Yeah, Aryan's saying proteins. Actually, I did take a course on nanobiochemistry in my master's, but I don't remember anything. Yeah, protein is a good answer. So yeah, these are proteins, and the way they are folded is very, very complicated. It's actually one of the most complicated problems of computational problems of humanity. We cannot really predict how these proteins fold and how they interact with each other because they're so long and there are so many parameters and interactions between them. So in order to understand them, we can break them even smaller. So, okay, what are proteins and RNAs and DNAs made of? Anybody knows in the audience? Excellent, Karim. So Karim is saying amino acids. So, okay, we cannot predict protein foldings very precisely or very rapidly, but let's see at least if we can simulate amino acids. So if you are in chemistry simulation, you know that in order to simulate a molecule like amino acid, you either need to have a lot of approximations like ab initio simulations or some simulations that have a lot of approximation and they're not precise, or you can try to simulate them precisely, but then the problem is that when the molecule gets bigger, there are so many electrons and protons that are interacting with each other that if you don't want to use any approximation, this problem gets so complicated that with density function theory or DFT simulations, you cannot really predict big molecules. So just to put it simply, with classical computers, we have a lot of challenges in solving chemistry problems, protein problems, biology problems. And 40 years ago, 1980s, a couple of scientists very smart and inspiring scientists such as Richard Feynman, Paul Benioff, and Yuri Manin from different parts of the world, they said that, guys, look, like these classical computers are working based on switches and zeros and ones. A lot of our problems in the universe are just quantum mechanical by nature. So if we want to solve this problem effectively and efficiently, we better have a computer that by nature is built of these quantum principles. So we can go and map our molecule on the computer as it is. We don't need these so many approximations that make our predictions inaccurate. Now, they started this 1980s, right? This was just an idea in 1980s. And the question then was, but how to build this quantum mechanical computer? Like, what do we need to build this quantum mechanical computer? So I would like to ask from the audience, what are some particles that you think could be, let's say we are in 1980s and you are a scientist and you want to build a quantum computer. What are some of the quantum particles that you think could be useful for building a quantum computer? Ariane is saying electrons. Okay, that's a one really good answer. Sina is saying photons. Jamie is saying photons. Excellent answers. So yeah, ions, electrons, and photons are all quantum mechanical particles that we can build quantum computers with them. But since you are all, some of you are from tech background, keep in mind that we are also using electrons for classical computing, right? The difference in classical computing is that we are just using the electron transport. Like if electrons are transporting, the transistor is on. If they're not, the transistor are off. So we are not really leveraging the quantum mechanical properties of electrons. With quantum mechanical computers, we are really leveraging quantum mechanical properties of photons and electrons. So we are using principles such as superposition and entanglement, and we're going to talk about some of them later in the lecture in these computers. So we need to isolate them. We need to be very careful about noise and many other challenges to be able to build these quantum computers. So if you're interested in the hardware part, we can discuss that later in the questions, but I'm just going to go through a simple example to demonstrate the power of quantum computers and why building quantum, let's say we build it with these particles and let's say we solve these problems, but what is the advantage? So I see in the chat box, Sina also mentioned molecules and Mehmet mentioned entanglement of any quantum objects. They're all good points and they're really relevant to quantum hardware. So on the left side, we have our classical computer, right? Built with a transistor, and a transistor is like a switch. It's either on or it's either off. So we map that on and off to 0 and 1. It's either 0 or it's either on. Now, the question is, what about the quantum computer? What is the state of bit in a quantum computer? Anybody has any ideas? It's not a simple question. So what would, like if we transistors, we said transistors are like switches, right? Like a light switch. You turn it off, you turn it on. Okay, they're super small, but what about quantum computers? I mean, we said one of the problems is with the zeros and ones, right? Okay, so we are getting some good answers here. Sina and Shams are saying probability. Yes, that's a very important. Jamie is saying superposition. Yeah, excellent points. So with a quantum computer, your information is in a state called quantum bit or a qubit. Okay, so to simplify it, if you imagine a transistor, a classical computer as like a coin a quantum computer, like a classical computer, as a coin that is either head or tail, a quantum computer is basically like a coin that is constantly spinning. So it's neither head nor tail. Now, this is a little bit vague, right? If you want to do computation, we need a more accurate representation. So what scientists do is that they define this environment or this sphere, and they call it Bloch sphere, and they use coordinates to locate the state of your quantum bit. So this is something really something that it's good to remember. One of the main differences between a classical computer and a quantum computer is that in a quantum computer, you just don't have zeros and ones, you rather have a qubit. Now, the question is, if this qubit is neither 0 and 1, and if it's in a mixed state that is called superposition, or somewhere in between 0 and 1, then how can we read it with our classical computer? Well, there are so many options in that sphere, so that equation might be very complicated, right? So the question is how to get the answer of your quantum computer on your classical computer if it's not classical. What do you think? I'll rephrase the question, and I expect answers from everyone because we simplified as simple as a coin, right? So if, let's say you have a coin that is either head or tail, and we have another coin that is constantly spinning, right? So classical computers only understand head and tail. Quantum computers are like coins that are constantly spinning. If you have a classical computer, how would you read this information from a quantum computer? Okay, I think it's a difficult question. So the answer is that once you're working with your qubit, you need a quantum computer to manipulate and change the state. So once this coin is rotating, you need a quantum computer to change the state of it, change the phase of it. But once your computation is done, you do what is called a measurement. So once you do a measurement, this spinning coin will become either 0 or 1. And that's why you can read it with your classical computer. So now, like right now, after this session, you can sign into IBM, you can sign into Google, you can sign into D-Wave, run a code on their quantum computers and read it on your laptop. Yeah, isn't that cool? So I hope that's clear how the transfer of information from quantum computer and classical computer works. Ariane is asking an excellent question. Is it predictable and always giving the same answer? Excellent question. Okay, the question is predictable with what? And the question is, what is the problem? So I'm going to answer that a little bit later in an example, Ariane. And if I didn't cover it properly, feel free to ask your question again. But we are going to go through it step by step. Thank you for your question. So let's say you have two classical bits on the left side of the screen. They're like coins, head or tail, and two quantum bits, which are like spinning coins, on the right side of the screen. Now, the question is, like, you know, with the coins that are either head or tail, at the same, you can be, let's say, head or tail or head. But with the spinning coins, how many possible answers can you get out of them once they are you know, stopped spinning? So how many potential options can we get from two spinning coins? Is it head or tail, tail or head? Okay, Ariane saying 4. So yes, so it's a very simple question. I think you all know it. With a classical coin or classical bit, at each experiment, you get one state, right? 0, 1, 1, 0, 0, 0, 1, 1. With the spinning coins, there is a probability of getting one of these 4 states, right? And once you have a quantum computer, you can manipulate these spinning coins so your answer will be one of them based on your problem. Now, with a classical system, you might need to go through all of these states to get an answer. With quantum computers, you can skip that by being in all of these states at the same time. Now, the question is, if we increase the number of qubits to 4 and increase the number of classical bits to 4 as well, how many states are we observing at the same time with 4 spinning coins? What are the options? Is it like, let's say head, 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 tail, head, head, tail, tail, head, head? If you count it, how many options do you get? And also feel free to use your microphone. Okay, Anaita is saying 16. That's correct. So once you have 4 qubits, thank you, Anaita. Once you have 4 qubits, you are basically you can have one of these 16 states as your answer. So before your coins are measured or dropped to a head or tail answer, there's a possibility of getting one of these 16 states. With classical example, you can get one answer at a time. So if you want to go through all of these options, you need to do your experiment 16 times. Now let's go to a more complicated system. Let's assume a very powerful classical computer, a gaming computer or a very powerful laptop. Sure, if your laptop. So the question is, how many qubits do we need to go through all the possible states that you can get with a powerful classical computer? So classical computer has one trillion transistors, and oh, we have really good answers here. So the question is, how many qubits do you need to get all the potential answers from a very powerful classical computers? So Azad is saying 2 to the power of n, and Anaita log 2 of that. Shams is saying 40. Now, yeah, that answer is correct, and I'm very impressed how fast you got that answer. But basically, with 40 qubits, you can be at all these possible scenarios that you can get with a classical computer with trillion transistors. So if you can get 40 qubits, there are some problems that you can solve more efficiently than a super powerful classical computer. Now, this question would get very, very interesting and maybe historically important if we can beat the most powerful supercomputer on our planet. So our most powerful supercomputer on our planet, as far as I know, is IBM Summit. It has 73 trillion transistors. The question is, how many qubits or quantum bits do we need to beat these super powerful classical computers? And again, the answer is, in the 2 to the power of n. But any guesses? See, I'm saying 42, very close, very close. Ariane is saying 45. So, okay, the answer I'm gonna give you is based on also errors included. So some of you might give a good answer, but you need only 53 qubits to beat the most powerful super classical computer on our planet. And that's really impressive because once you go beyond that, you might be able to solve problems that we could have never imagined before, because we have never had anything more powerful than that. Now, the question is, where are we? Have we been able to get to that stage, to get to 53 quantum bits and beat a classical computer? Anybody knows? I'm gonna try to wrap it up soon. I mean, so this is a very exciting question. Like, this is a question since 1980s. When are we going to be the most powerful classical supercomputer? Okay, so in 2019, an experiment led by Professor John Martinez from the University of Santa Barbara and head of quantum computing at Google, they led an experiment that they demonstrated that you can beat a classical supercomputer with 53 qubits. They used a very particular example to demonstrate that they could solve a problem that takes a supercomputer many, many years, and they solve it in a couple of minutes. So I'm just gonna check the question. Yeah, Sina is saying quantum supremacy is claimed, but for only once. Actually, another group demonstrated it in China a few months after that. So we have two demonstrations as far as I know. So if you are interested to know more about this experiment, I did an interview with Professor John Martinez. I'm gonna post it as at a podcast that we have. It's called Quantum Bits Podcast. We post interviews with scientists, entrepreneurs. We interviewed the founder of the world's first quantum computing company here in Vancouver, D-Wave, Jody Rose. Search for it on Apple, Spotify, Google, and you know, it's designed to be good for everyone from any background. So if you're in software, if you are in chemical engineering or any other field, it's designed in a way that is useful for everyone. So I'm not going to continue discussing that experiment, but where I'm going to go is that just imagine what would happen if we get to more qubits, like 300 qubits. That's equivalent to the number of particles in the known universe. So that's why quantum computing is so interesting, and there is so much interest in the industry, in the academia, because we might not have a lot of applications right now, but there is this perspective that in the near future we are going to be able to solve problems that we have never been able to solve before. So Amirjan, how am I doing with time? I can wrap it up here and leave it to questions.
I think it's better. I think if you wrap it up, that would be great, because we can. We want to give time for questions.
Sure. So I'm just going to wrap it up here, and I'm just going to say that I brought up this figure to demonstrate that you know, this graph shows that on the blue line it shows quantum computing capability, right? And the purple line shows the potential of classical computers, and this bottom line is time. Now, I think you already know the answer, but the question is that where are we in this timeline? Because once we get to this part that quantum computing is exponentially faster than classical computers, and I think now you understand why exponentially, because you saw like from 2 qubits to 4 qubits to 40 qubits, there was such a huge difference. So once we get to this area, there is a vast amount of opportunities and problems and challenges that we have solved. So because of this recent demonstrations, we have passed this critical point. So maybe 20 years ago, quantum computing was something debatable, but now we have the evidence that quantum computers can be faster than anything else that we have had with classical computing. And that's why it's such an exciting time and opportunity for all of us to contribute to this field and solve more challenging and complicated problems. So yeah, thank you very much for your attention, and feel free to ask any kind of question. This was more like an introduction, so we want to open the floor for questions from all of you.
Thank you, Parham. Do you need your screen?
Can stop sharing? Yeah. I might use it later though to answer some questions.
Sure. So before we get to the questions, there are two other things. We had some people joining us later after the introduction. I want to welcome them and ask them to introduce themselves. So we start with Nastaran.
Hi, sorry I was late. My name is Natran. I'm a research associate at SFU. I'm working on climate change modeling, climate change solution modeling with focus on energy transition. And thanks for your talk. It was really interesting.
Thank you. Actually, climate change is one of the very promising areas of applications of quantum. There are articles about that.
Well, that's nice.
Thank you. Zahra? Zahra, can you hear us?
Yes. Hi. Can you hear me?
Yes.
Okay. I'm Sarah Mahmoudous, and I'm a master's student at Memorial University, bioinformatics. I'm working on COVID-19 sequencer technology. And that was a great talk. Thank you. I really enjoyed it.
Thank you for coming. Mehmet, if you want to introduce yourself. Mehmet, can you hear us? Okay, he cannot hear us. Am I missing anyone? All right. Let's do the group shot and then we go to the question from Sarah A. So everyone who wants to be in the group photo, please turn your camera on. We will do a group photo shortly. Sorry, I'm trying to get things sorted out here. All right. Yes. Sorry. 1 second. Everyone who wants to be there, turn your camera on the count of 3. We're going to do a group photo. I'm going to count 1, 2, and 3. Thank you, Ariane. All right, we go to Sarah and then we go to Azadeh.
Thank you, Parham, for your interesting presentation. I didn't follow you all through your presentation, which I think part of it is because of my background. But what I got is that this quantum computing has a large and far way faster capacity than classical computers. It sounds scary to me, and it's kind of threatens the human need for human intelligence. What do you think about that? And my second question is, what are the obstacles on the quantum computing development? And where do you think we're going? Thank you.
Thank you, Sarah. Yeah, but sorry if some of the presentation was not easy for you to follow. I tried to make it as diverse as possible, but next time I'll make it even more. Well, thanks for the question. Really, really good questions. And this question we can discuss for hours and hours. But I just want to first say something, and that's at this stage, quantum computing is more complementary with classical computing. So there is that's how we see quantum computing right now. So they're going to help us solve some problems, not all problems, some problems that are hard to solve with classical computers faster than classical computers. So examples include chemistry. That's why I brought chemistry, because chemical compounds by nature are quantum mechanical. Another example, communication, secure communication. There is this concept in quantum computing called entanglement, right? So you can entangle qubits and make secure communication that if anybody break it, you will know. But there are some problems that, at the moment, they're just much more efficient with classical computing, right? So most of the companies right now use a hybrid approach. Thank you everyone for your notes on the chat, by the way. So they use classical computers to solve a part of the problem, and they use quantum computers to use the other part of the problem. So at the moment, there is no prediction that quantum computing will take over classical computers. I've not heard that from any of the scientists or experts in the field. The perspective is that they're gonna help each other, right? Now, you mentioned the threat. The challenge with quantum computing, and one of the areas that some people are a little bit concerned, is more security, secure communication, right? So with this example of coins that we had, the similar principle goes back to encryption, RSA encryption, right? So some of you are familiar with this. The reason that our Zoom meeting is secure and nobody can jump in and see us is that our data is encrypted, right? Now, one of the ways you can break this encryption is by factoring numbers. And these encryption methods use really long keys, like 2048 RSA key. Now, even now, you can break this encryption, but it's going to take 50 to 60 years. And most people are not concerned about that. Like if in 60 years, someone read your text messages or emails, okay, that's fine. It's not good, but okay, that's okay, right? So they're breakable right now, but it just takes so much time, right? Now with quantum computers, you saw the power, right? You saw how exponentially it was getting faster and faster. Now with quantum computers, if you just get to a couple of thousands of qubits, you're going to break these RSA codes in a matter of, I don't know, minutes or hours. So there's a lot of, attention from the government and a lot of security companies on building quantum-proof security principles. So they can protect their systems when quantum computers, become a reality. Now, your third question was one of the challenges with with quantum computing. That's an excellent question, but I don't know if I should go with that or should I first answer the other questions. Maybe I can touch on it shortly. The challenges.
Yeah, sure.
Oh, there are so many challenges and so much progress, but one of the main challenges is hardware, right? So these qubits are, okay. Some of these qubits work at minus 273 Kelvin, like almost zero, like Kelvin, minus 273 Celsius, almost 0 Kelvin. And one of the reasons behind that is they work with superconductors, not all of them, some of them. But the other reason is that they work with microwave frequencies and they are so sensitive to noise that you need to really protect them from any noise, right? The other problem is the interaction between these qubits. It's not classical. So because of these challenges, what happens is that you might get 50 qubits, but these qubits actually die after a couple of milliseconds. So it's like a coin that is spinning, it just falls after a short amount of time. Same with qubits. So if you hear in the news that there are like, I don't know, hundreds of qubits, okay, that's cool, but you also need to take a look at how good are these qubits. And making good qubits is challenging. making a large number of qubits is also very challenging. And the challenge goes back to the nanofabrication, quantum mechanical design. Are you going to use a laser? Are you going to use a superconductor? And by the way, there are a lot of companies that are doing amazing work here in Canada. There's Xanadu in Ontario. They're making photonic system. In Vancouver, there are two big companies, one in software, one in hardware. Canada is really a pioneer in this field, especially if you consider the population. Yeah. Thank you for your question.
Sorry. Okay, next one goes to Azadeh. And oh, by the way, before we go to Azadeh, and this is, you don't have to answer
sure.
it now. Payman, Parham, sorry, Parhamjan, we need just a reminder to tell you, to ask you for what our takeaway should be from this meeting, and you don't have to answer it now, you can answer it at the end of the meeting.
Sure.
Now we go to Azadeh.
Okay.
Azadeh.
Thank you so much for your presentation.
Thank you.
My question is mostly about the quantum computing system. I was
Okay.
wondering when they will be commercial, like the laptop that we are using every day. And how about the size of this quantum computing? Because you show us a picture and the size seems so huger than what actually we see for the transistor-based computers. So I'm just asking. I know that the future is with quantum computing, but in terms of building the physical system or to be more commercial,
Right.
how is the roadmap for the future? Is it the only hype for the quantum computing right now because people think that this is the only way that solves the problem? I mean,
Right.
It is not the other way, that maybe there is no need to use it. I mean,
Okay.
of course, quantum computing is good, but they have also some drawbacks. I would appreciate if you explain more. Thank you.
Sure. Yeah, excellent question. So first of all, we are living in a very exciting moment. As I mentioned, in 2019 there was a significant achievement in quantum computing field, so they can really do something. But the good news is that right after this presentation, you can go to your web browser, and based on your preference, you can choose whether you want a quantum annealer or a Rigetti quantum computer or a photonics quantum computer. So you can search for D-Wave, you can search for Rigetti, you can search for IBM quantum, you can search for Xanadu. You can go to their websites, and some of them provide free access. They are making this so accessible that, as I mentioned, we build apps and web-based tools for learning that really use these quantum computers, right? So these companies really want to, not just companies, like the whole field, want to get people engaged, right? So in order to do that, they build it in a very simple, interactive way. A lot of them actually use Python nowadays to interact with the quantum computer. So you can go to their website. I wish there was time for me to walk you through this. Maybe I can do that future in another opportunity or in another program. We are working on this. But you can go to their website and try coding your own quantum computing program, and you can do experiments.
You mean the ones that actually they built in IBM or for Google, right? Yeah, you mean we can connect to them and work, right? Something like this?
Yes, they don't give access to all of them. So in case of D-Wave, you get access, I think you get access to their 5,000 qubit quantum annealer for free, just for a little bit of amount of time. If you need more time, you can buy it from them. Or you can contact your institution or university to make a contract with them. Same with IBM, they don't give access to their fastest one unless you ask them, or if you're a company, you want to work with them, but they have like 5 qubit systems, 9 qubit systems that you can use for a certain amount of time for free. Now, to talk about the scale of a quantum computer, if you are interested, I can show you one on my screen.
I appreciate it.
Okay, so let me see. So I'm going to show you the quantum computer in here in Vancouver. That quantum computer actually uses a different system. It's called quantum annealing. So it has more qubits, but this is a visit I had back in 2016 to their hardware quantum office in Burnaby. So as you can see, it's quite large, right? The question is, what is in that large box? Why it's so big? Now, if you go inside, and sometimes actually, you know, some of them, they are being repaired. You can go and have a look inside. You can see this kind of chandelier-looking object. And basically, this is a fridge. So this particular type of quantum computing works only at very low temperatures, close to minus 273 degrees or millikelvins. And in order to get there, you need a lot of equipment to bring down the temperature. So this thing, the job of this basically cryogenic cryostat is to bring the temperature step by step down to, I don't know, 15 millikelvin or so. And you need to also put it in a box because you know, you want to shield it from electromagnetic waves and et cetera and et cetera. But the chip itself is down, you know, let me draw it. The chip is actually down here. So this is the chip. So the chip itself is actually quite small. So all the qubits are there, right? And yeah, if you are interested on Quantum Bits podcast, we have an interview with the founder of D-Wave. He talks about the hardware and you know, how he started the company, what are the challenges, what are the advantages, and you can learn more about his experience. But I just want to add that there are other types of quantum computers that don't work in these temperatures. For instance, there are type of quantum computers that work with photonics. There's a company in Canada, in Ontario, that use that technology. They don't need to, they can work in room temperature.
And how about their price?
So, okay, at the beginning, they used to sell it, right? D-Wave used to sell it for a couple of $1 million. NASA bought it, Google bought it. But nowadays, they have shifted to a cloud approach. So instead of selling you the quantum computer, you're doing a cloud approach. So you can get access to the quantum computer using an interface, which is based on a very simple, I don't know, familiar language, I don't know, Python or Q# or something like that. And, or each company has their own version. Cirque is for Google, Forest is for Rigetti, Strawberry Field is for Xanadu. So you can use these programming languages. So you can, you know, you can connect your problem to the quantum computer, and inside their system, they will convert it and convert it and convert it to more and more simplified, more relevant code, so the quantum computer can understand it. So all you need to have and know is your laptop and just some simple coding language and some basic understanding of, you know, quantum gates, I don't know, quantum, like entanglement, X gate, Y gate, Z gate, which you can learn. It's not that difficult to learn. If you want to use it for a certain application, if you want to build a quantum computer or algorithm, okay, that's a different story. You need to invest more time.
Thank you.
You're welcome.
Thank you, Mehrsad.
Sure. So thank you for the presentation. I had this more general question. So as you know, like we were using some of the reinforcement learning algorithms
Yes.
because it is almost impossible to just go through every single, I don't know, like a scenario and calculate the cost. Or like as an example, we're doing ab initio simulation, which is a simplified version of the real world, because because the real world is super complicated and we have some computational limitation.
Correct.
So I was wondering, in the future, when we get quantum computing, so what would be the future of these fields, or how they can collaborate to make progress?
Well, excellent question. So actually, you mentioned reinforcement learning, you mentioned ab initio simulations, and artificial intelligence in general. They are all one of the very good candidates for quantum computing right now. So So for instance, with reinforcement learning, this experiment done by the Martinez group, for instance, is capable of generating training data at a scale and size and entanglement that is not really possible with classical computers. So you can generate, random noise or training data for your reinforcement learning applications at a much better scale. Or there are lots of interest in tensor networks and neural networks or problems like traveling salesperson. These are one of the most preliminary applications of quantum computers. So to simplify it, for instance, let's say you want to go from Vancouver, I don't know, to Tehran, and you have so many options. You can stop in Frankfurt, you can stop in Toronto, you can stop in South Africa, and then you can stop again in Turkey or Dubai. So you have all these dots, right? And there are so many options, right? It's, I don't know, 2 multiplied by blah blah, or 2 to the power of 3 to the power of 2. There are so many options, right? And the more your stop points, the bigger your options, right? So one of the questions that quantum annihilers, for instance, D-Wave in Vancouver, can solve very effectively is this problem, like traveling salesperson problem. But there are applications in neural networks and AI that can leverage the same principles to solve these problems faster. So yeah, I don't know if that answered your question, but it's one of the early applications that is already being investigated. Is there any evidence of advantage? Like, is there any AI algorithm that has been solved faster with quantum computer than a classical supercomputer? Not yet, but we're very close.
Thank you.
Yeah.
Thank you. So I think the next person is Sina.
Thanks for the talk. I have 2 related questions, actually. One is that we talked about the hardware. So we have
Yes.
the qubits, they work. What about the software? My knowledge should be a little bit old right now, but do we have all the logical gates that we need to program something in quantum computers? Like, I don't know, AND, OR, XOR, NOR, XNOR, every logical gate that we have. And then the second question is actually what you mentioned, that right now we can't interact with quantum computers using, for example, Python. So we are using classical computers to interact with quantum computers. Isn't that a limiting factor? Basically, we are thinking of quantum computers in terms of classical computer. Shouldn't we change the way we think about the computers and how we interact with them and how we just program for them?
Okay, that's a good question, and I think the answer to the first question will kind of answer the second one as well. But before that, I'm just going to share a link to an example of a traveling salesperson. Very simple, uses a real quantum computer here in Vancouver, D-Wave, minus 273 degrees for free. You don't need any coding, it's just an example. Well, thank you very much for your question. That was a really good question, actually, and I hope we had time to go through it more in depth. But what is very interesting about quantum computers, which actually came into your second question, is that in terms of model, like classical computers are modeled in gates, right? And, or someone proposed these ideas, right? XOR, NOR. With quantum computers, that's not how we look at them. And that's why we need a fundamental new perspective to the whole field. So quantum computers, one of the models to use and leverage this hardware is called gate-based model quantum computing. And it uses gates that are not OR, that are not XOR, not classical. The only gate that is classical is NOR, I think. So the quantum gates are different. For instance, one of the quantum gates is Hadamard Gate. So Hadamard Gate will put classical bit into a superposition state. So if you give it 0 and 1 to a Hadamard gate, it will go into superposition. And your answer from that will be random. There are other gates that will change the phase of your qubit. So you remember that sphere or ball? Before you measure it, this state of qubit is somewhere on that ball. You can change the phase of it. You can flip it. You can entangle different qubits. So it was a really good question. You can actually search for gate-based model quantum computing. There is a lot of content, and there are different gates that you can learn to use to solve your problems. And actually, if you want to use a quantum computer to solve your problems, it is necessary to understand these gates, what they do, and how you can solve your problems using this gate. So to answer your second question, yes, we don't look at quantum computers totally classical. We have to go deep into the gates. We have like scientists have proposed new gates, new models. We have totally new algorithms. Quantum algorithms are totally different with classical algorithms. Examples: Shor's algorithm, Grover's algorithm. There are search algorithms that truly leverage, because if you want to really leverage this power, you wanna use the gates, you have to think about new algorithms, right? So there's like a search algorithm that you can use to do searching faster. Or there are a couple of famous examples that you can actually learn really fast. Some of them are Shor's and Grover's, but people are building more and more new quantum algorithms, and we need them to be able to solve our new problems. Was that did that answer your question?
Yeah, actually. Okay. Thank you.
Thank you. I think the next one was Aryan, if I'm not mistaken. Yes. Aryan.
Yeah. Hello. I was looking to how to raise the hand. Sorry, in Clubhouse it's easy here. It was really hard to do so. Okay. Thank you for the talk. It was amazing. I got this question about the entanglement. Can we actually use it to send data over? Has there been like any study on that? To use it like as a means of communication?
Yeah, so it's quite impressive that it really works. But yeah, people have tried entanglement for quantum communication. There's something called the Bell state. So they use a Bell state. It's a very simple circuit. Yeah, it's just takes it. You can easily learn it. So they use that circuit to entangle two qubits, and then once they're entangled, you can have secure, super fast communication. So there have been a lot of demonstrations using entanglement for quantum communication. And that was a really good point. I actually really like to talk about entanglement. Thank you for bringing that up. But I just want to revisit the entanglement. It's a really cool concept. So basically, it says that if you have two qubits, if somehow you can use an experiment to entangle them, once, let's say this qubit is on Vancouver, the other qubit is with, who is this guy who went to space 2 days ago? Richard, the founder of Virgin Atlantic. He went to space, right? So we entangle these qubits and we give it to him. He goes to the space. And the moment I observe my qubit, his observation of his qubit will be affected immediately. I think faster than the speed of light, which was a really, really controversial topic for a lot of physicists. So you can actually leverage this property of quantum mechanical objects entanglement for your computation. It's really there. Like you can connect with the IBM Q quantum computer, entangle two qubits, run your problem. It really works. It's very impressive.
That's awesome. All right. Guess no other hand is up. So if anybody wants to jump in, do it. If not, maybe you can share the takeaway.
Well, yeah, I just want to say it's a really exciting time in the history of computing, and quantum computing. So, you know, it's not really that complicated. I mean, of course, understanding the whole field and building a quantum computer is super complicated. But there is something in it for everyone, right? Even if you're an artist, environmentalist, sociologist, artist, I said already artist, I like art, engineer, you work in NVIDIA, there are a lot of applications. I think NVIDIA made a simulator. So, you know, don't be frightened. You know, there are a lot of resources nowadays. It was not like this 4 or 5 years ago. So just search for your field and quantum computing. There's definitely an article about it. And a lot of them are really, you know, relevant. So they might not be solving big challenges right now, but everybody is trying to, you know, plan how to, you know, make the best out of this technology to solve our problems. So don't be scared of it. Go and try it. There are a lot of resources available online.
Thank you. And I appreciate it if you can send me an email, like, or send me a message with the
Sure.
version of it.
I'll simplify. I'll make it classical.
Thank you. Yeah, folks, we have another 12 minutes and you can take advantage of that. And somebody clapped, Ariane. Yeah, or if you want to talk about other fun stuff, I didn't mean to cut you short, but I wanted to give time for people to engage in the discussion. So if you want to share some of those things that you wanted to share and I cut you short, yeah, 10 minutes to do.
I don't know if you have any questions, any brainstorming, anything, feel free to share it. We can talk about it. It's very interesting that where quantum computing is in such a diverse area as quantum computing is really going these days. Like, you know, I mean, you work in air like flight systems, right? So that's one of the very early applications. Like D-Wave works with Boeing. Yeah. So, you know, it's very difficult to manage so many airplanes coming into an airport and, you know, optimize them. So optimization is one of the very early applications of quantum, and D-Wave is already working on so many problems on optimization. Actually, Boeing is one of the customers, Volkswagen is one of the customers. Again, I sent something in the chat. You can
Please
go.
do. That's interesting.
Yeah, I mean, it doesn't have the airplane example, but you can get a sense, you know, on how it can. It's one of the tools we built for our program. So you can choose Vancouver in the bottom, and it shows how you can find the fastest route between different locations, and it uses a real quantum computer. So it's just an example of the traveling salesperson or optimization. There are other examples there, like nurse scheduling, games, etc. I think Sina has another question.
Yes, Sina.
Yeah, actually, you talked about encryption.
Yeah.
That we can just break the encryption that we have right now based on RSA, I don't know, 512, anything, within minutes or seconds.
Not now, right? Like
not now, but if we have computers, we can break it.
Right.
So I think one of the most important topics in the quantum computer world is quantum encryption.
Right.
And where are we on that? Are we going to, I don't know, destroy all the basics of security on internet when we reach that point that we can use quantum computers to break the encryption? Or are we going to have a quantum encrypted algorithm before reaching that point in the quantum supremacy? I don't know if I could ask.
Okay, I kind of understand what you're saying, but correct me if I didn't get it wrong, if I got it wrong. Okay, so at the moment, well, with this 50 qubits, we cannot break really any complicated encryption code. The problem is that these qubits have a lot of error, right? They're not perfect. They are very sensitive to noise. They die really fast. So even if we get hundreds or thousands of qubits, they're not really perfect. So we need even more qubits to correct the error of those other qubits. So we need lots of qubits. It's a field in quantum computing called error correction, right? So to get to error corrected quantum computers, I mean, nobody knows when they will come out, but it's hard to see them in the next 5 years, maybe 5 to 10 years. Average of people in the field, you know, there was a survey, average of scientists and people in the field, that's what they believed, hopefully in the next 10 years. I hope that answers a part of your question, but what we are doing in the classical field, what is happening in the encryption society is that they're trying to get prepared for that early on, right? So they're using this time, like the next 5 or 10 years, to update the existing encryption methods so they will be quantum proof. So once quantum computing comes in, they're not going to be broken, right? And at the same time, they are also working on quantum encryption, like quantum-based encryption methods, like using photonics or entanglement or quantum communication methods. So there are a lot of interesting examples. One of the very famous ones was a demonstration in China. They use a satellite to do a video call using quantum communication, which is to some extent quantum proof in terms of, you know, breaking the encryption. But there are also classical methods to, you know, make them more resistant to the next 5 or 10 years of quantum progress. Does that answer your question?
Yeah. Thank you.
Yeah. So I would say don't worry for now. All the people, like the governments, these software companies, they're very careful about that. They're trying to update their encryption, but we don't know. We don't know. Maybe there will be a unexpected discovery.
Yeah, you know, it's a race. So someone might get it there before anyone else, and then they won't say it. So who knows?
Yeah.
Awesome. All right. Anybody else wants to ask one burning last question? All right. Seeing none, I am going to. I'm going to ask you about non-quantum aspects of real life.
Sure.
Especially in light of an email that I got from you yesterday. So basically, how do you find balance in your life? Because you're dealing with some very sophisticated quantum stuff that is cutting edge, and I'm very impressed. I kind of feel like it opens a whole floodgate of information for me. How do you keep the balance? Because this is a lot to digest.
Well, I think I really enjoyed this field from the beginning. And the reason I brought that first slide is that, like, you know, from childhood, this was most like a personal interest for me. So I never feel like I'm really working or, you know, I'm getting tired of doing this. Like every time there's a presentation or talk, I'm very passionate to, you know, meet people and share with them this. But I would say the challenge for me is more like a personality challenge. You know, sometimes you know, from the society there is this you know, perspective that you gotta be in one thing, especially in the academic environment in PhD. So you either have to be a scientist or an artist or a biologist or a spirituality or something like that, right? So I think this external perspective always caused a lot of questions for me. And what really helped me again was the biography of a lot of polymaths or scientists like Avalysina, Leonardo da Vinci, a lot of people. So if you read the history or biography of people who really did something impactful, a lot of them were active in many areas. I prepared some slides from Salvador Dali. For the end of the presentation, there was not enough time, but that's okay. But even someone like artist like Salvador Dali, if I watched the interview of him, they asked him, who are you? Like, how do you define yourself? And he was saying every person is an expression of their own cosmos or microcosm. And this artist is an expression of this artist is an expression of that. And that's how he introduced himself. He said, I'm an expression of nuclear age, atomic age, and a new era of atomic mysticism, right? And I was very shocked. Like, we know him as an artist, but he introduced himself as a kind of physicist. And he used to say, my father is Dr. Heisenberg. Heisenberg is one of the founders of quantum mechanics. So something that really helps me is to, get around this idea of, you have to be either this or that or that. I try to read about these people and remind myself that's not always the case. Like, it's okay to be sometimes, do different things and be in the middle. Does that answer the question? That was an excellent question, by the way. Thank you for asking that. It helps me to know myself better.
Thank you so much. That was amazing. Well, this is it. I'm going to stop the recording now.